Hello there, good evening. Thank you for coming and thank you to the organizers for accepting my talk. Today I'm going to talk about a topic that they may seem a little bit technical or rather restricted to the kind of, I don't know, the field of particle detector models, and possibly many of you, just from the title, will think that this is not interesting to you. But actually, while we were working on it, we ran into many issues that are actually, I think that they have like a wide range of applicability to whatever situation in which you have frictions with the locality. So I would ask for you to like at least listen to some of the observations that we made. So, well, first, let me tell you a little bit the story that you've heard many times today. Detector models are like devices or like thought experiments you want, or like perhaps something more realistic, that they allow us to discuss many aspects of quantum field theory in both flat and curved spacetimes. They provide us with operational approaches to local tasks, such as thermometry, like how do I build a thermometer, or measurements in quantum field theory. But it's also a natural ground for discussing the transmission and processing of information, both quantum and classical, by means of quantum fields. But why do we want to use quantum fields for transmitting information? Well, the reason why is that the quantum field theories are the only objects that we know satisfy exactly relativistic causality. That is, they actually have a sharp lightcone, and we would like to know if when using detectors as a way of like approaching some of these tasks in an operational manner, they respect the basic principles of relativistic causality when it comes to signaling, right? And in this talk, I'm gonna discuss a little bit the recipe that we've been using for like talking about general detector models. They're in some aspects they're not as general as the ones that Rick was talking in this morning. In some aspects they're perhaps a little bit more, and they basically this is a recipe that can be used to like collect many of the things that have been done in the literature in the past. First, you choose to couple to some observable of the field. In this talk, it will be only the field amplitude, and you couple some operator that has to do with the detector degrees of freedom. Then you integrate this Hamiltonian weight, if you want, over space-time slices, and then you construct a scattering operator by doing a time order exponential of this Hamiltonian. Examples include the usual unrooted DeWitt model. You can check that this is actually the rather distribution that the upon-like detector fulfills, that when plugged in here gives you the usual unrooted DeWitt model. The kind of models that, for instance, Rick was discussing this morning are things of this type. I don't know if you're into the literature of these things, perhaps you will remember that one of the first papers that were discussing this kind of stuff was done by Bill Unruh and the Wolf back in the day, in which they were discussing how is the interaction of a quantum particle that is non-relativistic with a quantum field in a way that more or less mimics the behavior of atomic systems, or like particles in boxes, whatever, with the quantum field. And in that case, the current is simply given by, well, simply, I wouldn't say so, this object here. Also, I should mention that this also was inspired for accommodating or comparing approaches to measurements in quantum field theory and protocols in quantum field theory, in which one uses a quantum field as a detector, in which case we just plug another scalar field of some sort that couples to the quantum field locally through some space-time smearing. And this is the topic that I wanted to discuss today. Okay, so we've been talking about, okay, no, I plug it here, this region of space-time, this detector, and I can access local information about the quantum field. But if you noticed, many of the people that were saying that, then they were putting Gaussians, or like they were doing things that were band limited and stuff like that. So there is a friction with that when discussing signaling and causality overall when you're doing these kind of things. But why do we do that? It's not only for simplicity, like I'm saying in the third point, also in effective models, such as atomic models, the best we can know is overall for potentials. There are powerful theorems that tell us that actually the orbitals of an atomic system are exponentially localized in some region of space, I would say. But they cannot be compactly supported because that would have like some implications at the mathematical level that are not desirable. Also, and this is something that may touch the hearts of some of the people here, in materials, if you want to use a detector as a material, or in other quantum fields, we don't know the structure of the field at all resolutions. We would like to know what happens if we just use a detector up to some resolution. But then you will realize that that's in strict friction with the concept of strict locality. I have this interaction here. So in the case of detector models, what I wanted to say is that since detectors interact with the field everywhere, there is no notion of them, for instance, being space-like separated. If you plug a detector with a Gaussian and you plug another detector with a Gaussian, they're both everywhere. So how do we discuss this business of the detectors being independent in terms of space-like separation? However, given that these things that I was saying before are sensible, at least to first-order approximation, we should be able to retrieve somehow an effective notion of space-like separation through an operational approach, and that's what I'm going to discuss today. I would call this signaling that happens against the assumption that the detectors are not compactly supported when we're using something, for instance, like a Gaussian. There is we're assuming that it is localized in, I don't know, like 3 sigmas, apparent faster than light signaling. I call it apparent because it's not faster than light signaling because the detector is everywhere. But it's apparent because it's against the assumption that it's compactly supported when it's not. I would bring to your attention that causality and signaling are difficult notions even in statistics. I don't know if you're aware of the whole field of research that emerges not only at the quantum level, like process matrices, formalism, or quantum causal models, all that stuff, but even in classical statistics, the notion of causal inference is a difficult topic to grasp. So we're going to use a concept of signaling that is borrowed from these studies. That is that if we have 2 parties that are A and B, we say that A can send a signal to B if the local statistics of B depend on the free parameters of A. For instance, if I put 2 interactions with 2 detectors and I just look at one detector and depends on stuff that only characterizes the other detector, then this other detector can send a signal, basically because it can encode classical information in these 3 parameters. If you're familiar with the detector literature, you could, for instance, encode information in the coupling constant or the internal frequency of the detector, whatever. Then I would like to just put this slide here. It's based on this work that we did with Eduardo and Maria Papayorio. Because maybe some of you are thinking, okay, but the model was not relativistic to begin with. Why are you worried about the thing not being compactly supported and trying to see how you recover causality when the thing is not causal in the first place? Well, it turns out that if we work in perturbation theory, there's not much problem, actually. The microcausality condition for the field implies something that you could call the causal factorization for the scattering operator. That in the end implies that person detector interacted with the field in strict space-like separation to not signal to each other. And even more, for more than 2 detectors, the superluminal signal that happens because of the non-relativistic dynamics of the full system in concurrent with the detector are which are related to the so-called the shortest impossible measurement problem are not present. A detector, a leading order, can only receive signals from its causal past. So where is all this leading? When we think about causality, what do you think? This is the cause of this other thing. It seems like a qualitative statement, right? Either the thing is the cause or it is not, but it's not. There's not this notion of like it is a little bit the cause of this thing, unless you talk colloquially. For that, and because I don't know, motivated by all this business of like not having compact interactions to define an effective notion of causality, what we did is to build a quantitative signaling estimator based on quantum methodology. Given that we set a detector A signals, detector B can infer the value of the coupling constant of detector A through its local statistics, we need to encode this property, and we're going to use the so-called quantum Fisher information. I don't know if you're familiar with this quantity. It's basically something that is used to generate in statistics some sort of uncertainty principles when one wants to promote a parameter to a random variable. But what is important to know is that if the Fisher information is 0, one cannot estimate the parameter associated with that. With I don't know, like when you have a family of estimators that depend on some parameter, one can randomize the parameter and check if one can infer the value. If the Fisher information is 0, you cannot infer the value. And that's what we're going to use as a quantitative measure of signaling in this context. We calculated it. We just did it like you just take the whole evolution, you expand everything into the leading order, and you calculate the quantum Fisher information of the reduced density matrix, the local statistics of detector B with respect to the coupling constant of detector A. And what we got is that the evolution can be thought as a unitary with respect to the parameters of detector A, and that in that case, the quantum Fisher information will be given by the variance of this operator. That's a technical thing. You can check when the evolution is unitary, that the Fisher information is bounded by the variance. Let's take a look at this operator. This operator has here the retarded propagator of the theory, which is independent on the state of the field. That's some information. The signaling that you can transmit between detectors, a leading order, doesn't depend on the state of the field. All states send signals equally, which is a reminiscent of from the fact that we're using linear fields and there's superposition principle there. Also, we get that detector A can only encode information with through the average value of this current operator that we've defined, that basically tells us how the detector A is coupling to the field. And another feature is that we're using the variance of this object. I will okay, it's okay. To the technical point, just to tell you guys what we did, a natural question that happens here is, okay, you've given me this signal estimator. We gave expressions for the signal estimator into I don't know, like an arrangement of situations. We extended some results that Eduardo had in 2015 that were basically like was basically the seminal paper on this topic. We tried to, I don't know, do it for unbounded operators, so something that was not done. We tried to see how it worked for curved spacetime, etc. But everything was more or less qualitatively the same. So we just restricted our analysis to unroot it with the detectors. Whereas that the case of curved spacetime was a little bit complicated to handle in general, what we did as a proof of principle is to study the signaling estimator for the case of the flat spacetime, because there are strong results that one can derive in that case. What we showed basically is that if you have detectors whose spacetime smearings are exponentially localized and whose centers are separated by some space-time distance with some scales, then signaling follows these scales. Basically, you get some sort of effective lightcone. Two detectors that are space-like separated at a distance that is much, whose centers are separated at a distance that is much larger than, say, the typical size of each of the interactions, actually cannot signal to each other, and the decay is exponential. So in principle, this in flat spacetime, we can use this notion, operational notion of localization, to talk about these things. I would note that this notion of localization is, strictly speaking, non-Lorentz invariant, because I'm saying that something is an exponential is localized here. What I'm saying basically is that this value is greater than something. Another observer will say it's something different. But for an effective theory in a reference frame, it's something that we can work with. Just to finish, let me give you an example. This is the case. Well, we've been talking about what happens when you have a detector that is like extended in space. This is not a draw. This plot is not showing that. What it's showing is a pair of point-like detectors. This is space. This is time, and each plot refers to a different value of the frequencies of each of the detectors, of these internal parameters. And what we see here is that what is represented is the position of detector A, the detector that is sending signals to a detector B that is at the origin. So actually, you plot it in 3+1 dimensions. That's a very easy calculation, because basically you just have to calculate the linear Becher potential, which is given by a delta, etc., and you can just like plot the result. And what we see is that indeed this thing is following sort of as an effective lightcone. If the detector is here in space-like separation, much farther than the typical time of interaction of each of the detectors, this thing vanishes. And also in the future, that is, this also captures the idea that there shouldn't be retrocausation between the measurements. If you do a measurement with a detector A, that shouldn't affect that you're going to do another measurement with a detector B later. So this would be 0. Well, this one is clear because it's in resonance. And this would be the lightcone. It's the path lightcone only. It's not the feature lightcone is excluded. That's something that we are remarking here. So let me conclude, and I will leave you alone. We have motivated the introduction of a quantitative measure of signaling that may have other applications beyond like checking the regimes of validity of detector models, but I think that was the goal. Our signaling estimator can be used to extend operationally the notion of relativistic causality to situations where effective models do not allow for strict localization. Although we have shown that here flat angle with detector calculations, the formalism should extend to general hyperbolic spacetime as far as you can calculate the green function, and to general detectors. In more general spacetimes, as an outlook, I would say that there will be non-trivial interplay between the localization scales in different coordinate systems and these exponential bounds I was talking about before. Perhaps there should be a sophisticated way of like going around the proof because basically for proving the exponential bounds, you have to work in the Fourier space. So perhaps there is a micro-local way of talking about this. And just to finish, I would say that it was a technical problem that applied to a very concrete physical setup, or like a formal setup, or like you will have these non-local interactions between these detector models. What happens when they're not compact? But there is a way of reverting the role that these things are playing, and to think what happens if I have a field theory that is non-local because I have a cutoff, for instance. Can I think about local interactions, non-local interactions in a causal field theory as local interactions in a non-causal field theory? and see what the interplay is and how causality emerges. So that's all everything I have to say. I hope you enjoy the lack of equations. And thank you very much for listening. I will answer any questions that you have.
We're a little bit tight on time, so we only have time for one question. So I'm seeing, so I think we're gonna leave it there. Sorry.
I actually have two questions, but the first one is very easy. Can you come back to slide 7, please?
What?
Slide 7.
Yeah.
Thank you. Now, the second question is, there you have the expected value of JA, right?
Yeah.
I'm assuming that this is in the interaction picture,
Yeah.
which means that effectively, if detector A starts in a state such that that expected value is 0,
Yeah.
which, well, there are many states, then will the signaling estimator be 0? Does the segment
Yes.
deduced? What's the physical interpretation of this?
That the leading order, well, that is quadratic in the coupling constants, the influence of detector A into detector B cannot be affected by the fluctuations. If you think about it because the detector has to interact with the field, the detector A has to interact with the field, that is one insertion, and then the field has to interact with the detector B, that's another insertion. So you cannot take into account, the fluctuations cannot affect that from detector B.
Let's thank people again.